이번 섹션은 미국 산호세 SK 하이닉스 키스킴께서 DRAM과 SSD의 자동차 기능 안전 애플리케이션을 위한 설계 고려 사항을 발표할 예정입니다. 플래시 소자는 최근 수년간 다양한 응용 분야와 요구 사항, 특히 완전 자율 주행 차량에서 발생되는 방대한 양의 데이터를 저장해야 하는 필요 요건을 만족하는 소자입니다. 이번 발표에서 SK 하이닉스는 고신뢰성과 고안정성의 자동차 플래시 SSD 로드맵과 그 애플리케이션에 대한 자료를 소개합니다.
Keith Kim will present design considerations for DRAM/SSD for automotive functional safety application. Flash device has been sought after device in recent years for multiple different areas of application demands, especially as data storage needs for connected and fully autonomous vehicle continuously increase. Timely presentation from SK hynix will bring insight into highly dependable automotive flash SSD roadmap and its application.
Hello. First of all, I'm very honored to introduce myself to you. Thank you for inviting me to ASSIC 2021 event. I'm Keith Jang Kim, who is working for SK hynix America and responsible for the team leader of the DRAM technology group. I'm managing all DRAM product and DRAM technology in SK hynix US office. I have been with SK hynix for 15 years and has experience in DRAM design, test engineering, and product planning. I was leading SK hynix JEDEC memory specification for 6 years, and I was JEDEC committee DRAM function and feature chairman as well. I'm currently my focus area is enabling DDL, LPDDL, GDDL, HBM memory evaluation and designing, pathfinding future memory concept technology like post-DDL, post-LPDDL, post-HBM, and CXL memory expansion as well. The key title is Design Consideration for Automotive Safety Application. Automotive industry is advancing at rapid pace. The innovation in self-driving technology and functional safety is becoming more than a value-added feature in customers' mind, and is becoming more expected as a must-have feature. Today, I will explain the detail of requirements for semiconductor that is needed to support these new self-driving and safety features. So, as you know, memory is one of the key enablers for automotive driving, achieving the next level of the automotive and infotainment and connectivity requires computational power, which can be delivered by memory bandwidth and capacity. The safety feature of the cars are the most critical issue directly linked to human life and death. As a representative of SK hynix, which is a memory solution provider, I will give an overview of automotive specific target requirement, market trends, and challenges as a silicon provider. So first, I will give you a rundown of the automotive market, memory market, and memory target requirement in terms of the DRAM and NAND perspective. This slide shows automotive vehicle DRAM and NAND requirement. As some of you may know, the self-driving capability is split into 5 levels, from level 1 to 5, according to the self-driving functionality. Some government classify up to level 6, but we will mainly discuss the 5 levels as shown here. Currently in 2021, the mainstream cars are using level one or two, but some leading luxury brands are able to implement level 3 autonomous driving in their cars. Uh, Additionally, most of the automotive manufacturers are internally pushing for new car system architecture, which will take their product over level 3. Of course, the law and regulation will lead to catch up with the advancing technology, but we expect that perhaps in 2030 timeframe, there will be level 5 vehicles in public roads. In level 3, 4, 5, for advanced automotive or autonomous driving, many sensors and electrical processing powers are needed. Research by Yole suggests that about 30 sensors will be needed. Sensors need to undergo sensor fusion to merge and process the collected data, and memory will also play a key role here. Memory will not be simply a low capacity and low bandwidth commodity, but it will be a key component of automotive self-driving. There is a need to massively increase the bandwidth and capacity of memory in order to automotive the sensor and processing power behind each of cars. Because huge amount of the data should be gathered and huge amount of data need to be processed in real time. Therefore, the high bandwidth and higher capacity memory should be one of the key requirements in the future. The SK hynix recognize these challenges, and SK hynix is preparing new product and improvement to deliver on these industry requirements. This slide shows building an automotive memory development plan. If we examine the factor of the growth for memory in automotive application, there are three key sections. New vehicles will need to support over-the-air update such that vehicles can communicate real-time low data and traffic information. Also, continuous software and firmware update to the car infotainment and instrument will be required. To support this important telematics, high bandwidth memory will need it for the vehicle to communicate with its surroundings. Infotainment and digital cluster is an important part of the user experience. Different cars will have different OS support based on their target driver. Also, high resolution display support and real-time information to deliver mean that memory will play a big part of in driving this sector. Of course, when we move forward to automotive driving, that will be a most demanding factor in automotive memory. Human to machine interface and different driving metrics or many load condition will be important factor to process, and memory will be need support the increase in processing power data too. If we look at the memory spec requirements, we can observe that memory spec increase for automotive driving level. Like we saw in previous slide, memory bandwidth and capacity will increase as the level increases. As you can see, this memory trend and plan chart as we move from the ADAS advanced driver assistance system to autonomous driving level, memory density and bandwidth should be improved dramatically. From the level 3, generally use powerful single SoC and 8 to 2 gigabyte DDR4 DRAM up to 5 12 gigabyte eMMC or UFS NAND solution. From the level 4 that consists of the multi-SoC with the accelerator and use up to 64 gigabyte LP memory solution for SoC plus HBM solution for accelerator memory up to 1 terabyte UFS and SSD NAND solution. From level 5 that consists of the multi-system up to 100 gigabyte LP5 for SoC, HBM memory for accelerator up to 2 terabyte UFS, and SSD NAND solution. There are lots of the discussion in what types of memory that will be used in automotive sector, but SK Hynix expect that LP line of the memory will continue to become a dominant portion in automotive sector for possible future in order to meet low power, higher bandwidth solution. Definitely, HBM will be the dominant accelerator solution in the future. Slide 5, this showing the DRAM and NAND market forecast and transition plan. The automotive DRAM market is transitioning from DDR3 to LPDDR4, 4X rapidly, and some leading SoC and Tier 1 customers are looking to develop car with the LPDDR5 memory in the future. We expect LPDDR5 memory cost to be on the load by 2025 timeframe. For NVIDIA, leading SoC is driving the LP4 and LP5 with HBM X with their heterogeneous computing architecture. This dual memory will be paired with their SoC plus accelerator for the future customers. The automotive NAND market is transitioning from eMMC to UFS rapidly, and crossover will happen in late 2023 timeframe. SSD demand will be increased when autonomous level is increased, level 2 or level 3, 4, 5. So the latest generation of the vehicles are using the new electronic architecture to connect vehicle computers with the domain network. These domains are managed by dedicated domain control unit. This solution provides a reference design to develop the domain control unit by supporting a variety of the physical network and specialized power supply circuit for domain control, body, chassis, and gateway application. Because of the worldwide regulations on carbon emissions, many car manufacturers are transitioning to electric vehicle as their mainstream lineup. Autonomous vehicle technology will make their way into electrical vehicles, which will accelerate the development. If we look at this diagram here, current car have 100 of sensors, controllers for powertrain, ADAS, body, and IV in-vehicle infotainment, respectively. Each part has separate 100 of the ECU, electronic control unit. Now, new controller architecture for tomorrow's car will have domain controller with the central gateway, meaning that this domain controller will focus communication in each of these sensor controllers to centralized processing node. Future car will take this centralized concept further and will give a progress of the advanced self-driving. Many OEMs are exploring centralized or zonal architecture for their system. This will again mean more bandwidth and capacity requirement for the memory. Okay. Second, I will now talk about the challenges and considerations for automotive functional safety for both DRAM and SSD. So as I explained in the previous chapter, the changes to electrical and electronic architecture will become a more important consideration. There will be some tests for central or zonal architecture in cars, but eventually it will be get there. This means that the ECU will become consolidated, and bigger ECU electronic control unit will need memory with the higher bandwidth capacity that is able to support the higher processing requirements as well. Also, DRAM will be used in safety critical ECU such as a domain controller, gateway, autonomous driving, ADAS, advanced driving assistance system, and central compute as well. LPDDR4 and 4X is mainly used in the system, and LPDDR5 will be also used in this system is required to meet the automotive safety integrated level, B2D. SK Hynix is currently developing high quality product that meets the extreme requirements for human safety system. Therefore, memory company needs to account for this human critical system requirement and design for solution that will be compatible with high stress, high stake environment. This slide shows ISO 26262 functional safety not an option anymore. So we need to recognize that ISO 26262 is not optional but mandatory. The basic requirement in ISO 26262 is FMEDA failure mode, effect, and diagnostic analysis, and the fault and failure here can lead to systematic fault or random fault or failure. Random hardware fault and failure is only able to be evaluated through the FMEDA. Systematic fault failure can be mitigated building robust process and implementation. Compliance with the ISO 26262 requirement and effective safety analysis for prevention. Random fault and failure can be mitigated by implementing fault-safe design. Random hardware fault and failure evaluation uses a hardware architecture metric and probabilistic metric for random hardware failures to find probabilistic failure rate. So this slide shows challenging for automotive memory production. There is a different grade requirement for silicon for the automotive sector, but this is a general overview. There are different requirements which include operating range of from -40 degrees C to 125 degrees C, or sometimes even 150 degrees C. The DIS drivers information system, which is the infotainment system, needs from -40 degrees C up to 105 degrees C operation range. ADAS body chassis need to be certified from -40 degrees C up to 125 degrees C, and even 150 degrees C is needed for the engine, transmission, and powertrain silicon components. These factors are critical for the safety of driver and passengers, so quality and reliability must be certain to preserve human rights in emergency situation. Additionally, silicon component must last the lifetime of the vehicle, so additional time certification is needed. As I said earlier, functional safety in automotive application should achieve perfect level like a zero field failures from -40 to max 150 degrees C, ambient temp and 15, and max 20 years lifetime support. The design of memory should fundamentally take the safety and reliability consideration into mind. We list some example here is that, as I mentioned previously, FMEA failure mode and effect analysis, FMEDA failure mode effect and diagnostic analysis is now requirement. So evaluation of the failure fault must be completed at the system level. Also, multiple safety mechanism must be made for a probabilistic chance that something may go wrong. Regarding the spec to make a more robust product for our partners, we need to improve data protection and error detection policy. One of the keywords in industry is transparency to store the error information and deliver this error information in real time. Those are the industry requirements. The memory ECC in a way that is compatible with the system ECC, memory on-die ECC should be aligned with the system level ECC coverage as well, and have a fault injection test to verify in DRAM ECC circuitry operation is good or not. Additionally, traceability and consistency should be the key part of the product development, and we need to use design tool software that is in compliance with the ISO 26262. In the final chapter, I will discuss what SK hynix doing to meet the autonomous driving future. We will introduce SK hynix product lineup and share SK hynix roadmap and directive for automotive market. This slide shows a current automotive product portfolio in SK hynix. SK hynix is making various DRAM and NAND solutions to provide scalability for all segment and application. As the transition of the main automotive memory chain from DDR3 to LPDDR4, LPDDR-X, there is a new differentiation in the target segment, premium, mid-range, or entry level. Therefore, there are some differences in density and bandwidth. A leading SoC company is currently using LPDDR5, which is used in mobile premium segment to develop future automotive system. If we look at it by market segment, in telematics, ADAS, advanced driver assistance system, the market places more importance in memory bandwidth compared to density. For infotainment, CDC, cockpit domain controller, as a transition to autonomous vehicle take place, both memory bandwidth and capacity increase is required. Another key factor is that in centralized car electronic architecture for EV cars, power consumption is also major consideration. Therefore, this bandwidth, capacity, and power consumption needs to be planned for in advance for automotive market memory. The latest generation of the vehicles are using new electronic architecture to connect vehicle computer with the domain controller and move to centralized architecture. By changing the new electrical and electronic architecture, self-driving capability level goes up, DRAM bandwidth and density will be increased dramatically. As you can see, the DRAM long-term roadmap in 2020 time frame, LPDDR4 and LPDDR4X is mainstream. But from the 2025 time frame, LP5 and LP5X will be mainstream. And in 2030 time frame, post LPDDR5 or HBM will be the mainstream memory in automotive application area. This slide shows automotive NAND long-term plan. I already mentioned that by changing new electrical and electronic architecture and self-driving capability level goes up, automotive NAND solution type will be changed. As you can see, the long-term plan is in 2020 timeframe, eMMC 5.1 is mainstream. From 2023 timeframe, UFS 2.1 and UFS 3.1 will be mainstream. Max sequential bandwidth will be 2000 megabyte per second. From 2027 timeframe, UFS 4.0 and PCI Gen 4 will be the mainstream that can support up to 7,000 megabyte per second. From 2030 timeframe, PCI Gen 5 and UFS 5.0 will be the mainstream in the NAND application. The SK Group has developed an optimal setup technology and is ready to host an e-mobility era. SK groups are working together to lead the e-mobility era in the future, as we can create a variety of the synergies from automotive business perspective. It would be good to pay attention to how SK hynix and SK Group will lead the automotive business in the future. That's all I have for today's presentation. If you have any questions, please send me an email. I will answer you with all my heart. Thank you so much.